Hello friends, welcome to my lecture on origin and classification of first order partial differential equations, which we write in short as PDE. First we define a partial differential equation. An equation which involves partial derivatives of an unknown function of two or more independent variables is called a partial differential equation. These equations arise in connection with numerous physical and geometrical problems. The independent variables involved in such problems may be the time variable and or one or several coordinates in space. A first order partial differential equation in two independent variables x, y and one unknown z, also called dependent variable, is an equation of the form f x by z, derivative of partial derivative of z with respect to x, then partial derivative of z with respect to y equal to 0. If we write p equal to partial derivative of z with respect to x and q equal to partial derivative of z with respect to y, then equation 1 can be written as f x by z p q equal to 0. A solution of a partial differential equation in a region R of the space of independent variables, here we are taking them as x, y, is a function having all the partial derivatives appearing in the equation which satisfy the differential equation at every point in R. Let us see how the first order partial differential equation originate. So, before discussing the solution of a partial differential equation of the type 2, that is f x by z p q equal to 0, let us see how the partial differential equation of first order arise. So, consider the equation x square plus y square plus z minus c whole square equal to a square, where a and c are arbitrary constants. You can see that this equation represents the set of all spheres whose centers 0 0 c lie along the z axis and the radius is r a. Now, from this equation, when we differentiate it with respect to x, partially with respect to x, we get 2x plus 2 times z minus c into partial derivative of z with respect to x equal to 0, or we can write it as x plus z minus c into p equal to 0. Similarly, when we differentiate this equation x square plus y square plus z minus c whole square equal to a square with respect to y, we get 2y plus 2 times z minus c into partial derivative of z with respect to y equal to 0, and or we can say y plus z minus c into q equal to 0. Now, if we want to eliminate from this equation x plus z minus c into p equal to 0, y plus z minus c into q equal to 0, the constant c, then we can write it as x over y equal to z minus c into p divided by z minus c into q. So, we can say we get qx equal to yp or yp minus qx equal to 0. So, eliminating the constant c from the equation 4a and 4b, we obtain the first order partial differential equation by p minus xq equal to 0, which is a partial differential equation of first order. Now, in some sense, then the set of all spheres with whose centers lie on the z axis, here we are taking them as 0 0 c, is characterized by the partial differential equation by p minus xq equal to 0. Now, we shall see that the other geometrical entities like x square plus y square plus z minus c whole square tan square alpha, which represents the set of all right circular cones whose axis coincide with z axis. So, here we see you can see that the vertex of the cone lies at the point 0 0 c, the semi vertical angle of the cone is alpha. So, and the axis z axis is the axis of the right circular cone. So, this equation represents the set of all right circular cones whose axis coincide with the z axis, and when we differentiate this with respect to x, partially with respect to x, what do we get? 2x equal to 2 times z minus c into partial derivative of z with respect to x, that is p into tan square alpha, and when we differentiate this with respect to y, we get 2y equal to 2 times z minus c into q tan square alpha. So, eliminating the constants c and alpha, what we get? X over y equal to p over q, and this gives us the same partial differential equation as in the previous case. So, here we get again the same same partial differential equation by p minus x q equal to 0. Thus, we see that for these cones also the equation 5, that is by p equal to x q, is satisfied. The common thing between the spheres and the cones is that they are surfaces of revolution with z axis as the axis of symmetry. They can be generated, the sphere can be generated with z axis as the axis of symmetry, and similarly cone, the right circular cone can be generated with z axis as the axis of symmetry. Now, all such surfaces of revolution are characterized by z equal to f r, which is f of x square plus y square, where this is f z equal to f r equal to f under root x square plus y square, where r is equal to under root x square plus y square is the distance of a point of the surface from the axis of rotation. Say for example, you have this, suppose you take the sphere, you take the right circular cone, this is here the vertex is at 0 0. So, this is x square plus y square equal to z square tan square alpha. I have taken c equal to 0 here, and this is right circular cone with semi vertical angle alpha. So, here if you take any point on the surface of the cone, then its distance from the z axis, its distance from the z axis is, you can take the consider the orthogonal projection. If this point is x y z, then this is your x and this one is y. So, this distance is under root x square plus y square, and therefore, distance of the point x y z on the surface of the cone from the z axis, this is perpendicular, this is 90 degree. So, this is also under root x square plus y square, this one. So, r is under root x square plus y square. So, where r is the distance of a point of the surface from the axis of rotation. So, z is a function of r, and from this equation z equal to f r, you can see that when we differentiate this partially with respect to r, we get derivative of z with respect to r as f prime r, z equal to f r. So, f prime r into partial derivative of r with respect to x, and when we differentiate partially with respect to y, what we get? F prime r into partial derivative of r with respect to y. Now, r is equal to r square is equal to x square plus y square. So, you can see 2r del r y del x equal to 2x, and what we get? We get the derivative of r with respect to x equal to x by r. Okay. So, this is f prime r into x by r, and this similarly when you differentiate r square equal to x square plus y square with respect to y, you get 2r, the derivative of r with respect to y equal to 2y, and what we get? Derivative of r with respect to y is given by over r. So, this is equal to f prime r into y over r. So, you see f is equal to, this is p, this is q. Okay. So, p equal to f prime r into x by r, q equal to f prime r into y by r. And now, we can eliminate the arbitrary function f here by dividing this equation p equal to f prime r into x by r by the equation q equal to f prime r into y over r, and we get p over q equal to x over y. So, p over q p over q equal to x over y, which gives by p equal to x q. Thus, we see that the function z defined by the equation 3, 6 and 7 in some sense is a solution of 5, equation 5, this equation. Okay. So, now let us note that the relation 3 and 6, you can see the relation 3 and 6, this is relation 6. Here we have two arbitrary constants alpha and c, and here we have in 3 two arbitrary constants a and c. So, they are both of this type, f x by z a b equal to 0, where a and b are two arbitrary constants. Now, let us see when we differentiate such an equation relation in x by z containing two arbitrary constants, we are taking them as a and b, then let us see what partial differential equation we get from here by after we eliminate a and b. So, when we differentiate this with respect to x, what we get? Partial derivative of f with respect to x plus partial derivative of f with respect to z into partial derivative of z with respect to x, this. Equal to 0, or we can say so we get this equation. Similarly, when we differentiate the equation 8 partially with respect to y, we get and r we get partial derivative of f with respect to y plus partial derivative of f with respect to z into q equal to 0. Now, the equations 8 to 10, you see the equations 8 to 10 involve two arbitrary constants. So, eliminating a and b from these three equations, we get the equation f x by z p q equal to 0, which shows that the system of surfaces 3 give rise to a PDE 11 of the first order. The system of surfaces 3, the system of surfaces 3 or you can say 6, okay, give rise to a PDE of the type f x by z p q equal to 0. Now, let us look at a generalization of equation 7. This case here we are writing z equal to function of under root x square plus y square, and we got the differential equation of first order y p minus x q equal to 0. So, let us consider a generalization of this case. Here we consider f u v equal to 0, okay, where u and b are functions of x by z. U is function of x by z, say phi x by z, b is function of x by z, say psi x by z. Now, when you differentiate this equation f u b equal to 0 partially with respect to x, but you get partial derivative of f with respect to u into partial derivative of u with respect to x plus partial derivative of u with respect to z into partial derivative of z with respect to x, which we are writing as p, plus partial derivative of f with respect to b into partial derivative of b with respect to x plus partial derivative of b with respect to z into partial derivative of z with respect to x, which we are writing as p equal to 0. Similarly, when we differentiate f u v equal to 0 partially with respect to y, we get partial derivative of f with respect to u into partial derivative of u with respect to y plus partial derivative of u with respect to z into partial derivative of z with respect to y, which we are writing as q, plus partial derivative of f with respect to b into partial derivative of b with respect to y plus partial derivative of b with respect to z into partial derivative of z with respect to y, which we are writing as q equal to 0. Now, what we do when we eliminate the arbitrary function f from here, okay, you can see we can write this equation, this system of equations as the partial derivative of u with respect to x, in short we can write as u x plus similarly u z into p, then we get u y plus uz into q, and then second row we can write as bx plus bz into p, and then by plus bz into q multiplied by the column vector fu and fb equal to 0. Okay, so we can write these two equations in as a matrix equation, and then this equation will have a non-trivial solution provided determinant of the coefficient matrix is 0. So, we have determinant of this equation, this coefficient matrix equal to 0, that is that will give you ux plus uz p b uy plus uzq, then bx plus bz into p by plus bz into q equal to 0. So, for a non-trivial solution of this system, this matrix equation, we must have the determinant of the coefficient matrix equal to 0. Then when you evaluate the determinant, what you get? Ux by, then ux bz into q, then uz bz into p, uz by into p plus uz bz into pq, and then minus we have u by vx, and then we have u by bx bz p, and we have uz vx q, and we have uz bz pq. So, you can see uz bz pq will cancel with this uz bz pq. Okay, ux by minus uy vx we can write as ux uy bx by. The terms ux by minus uy bx can be written as ux bx uy by, and then we have here ux bz, let us take the coefficient of p. Let me write it on the right side. Okay, the coefficient of p will be equal to what we have, uy bz minus uz by, and the coefficient of q will be what we will have, uz bx minus ux bz. So, this is what we have, and we can write it in the form of the Jacobian. So, this is nothing but I can write it as in the form of Jacobian, delta ub over delta xy equal to p times, here we will have y z plus q times zx. So, this is what we have. So, we have p into delta ub over delta yz, then we have q times delta ub over delta zx equal to delta ub over delta xy, which is a PDE of the type 11. We can see this is a PDE of this type, fx by z pq equal to 0. We have p and q of the first degree, and then their coefficients are functions of x by z. So, this is the PDE of the first order, and it is of the type fx by z pq equal to 0. Now, this is a linear equation in p. You can see that p and q occur in the first degree, whereas in the equation 11, the p and q need not be of the first degree. So, this equation is a special case of the equation 11. Now for example, let us consider this equation x minus a whole square y minus b whole square plus y minus b whole square plus z square equal to 1. You can see this will when we eliminate the constants a and b here, it will result into this differential equation of first order, partial differential equation of first order, but it is non-linear. So you can see we can let us differentiate it partially with respect to x. We get 2 times x minus a plus 2z into p equal to 0, okay, and this when we differentiate it partially with respect to y, what we get 2 times y minus b plus 2z q equal to 0. So what we get x minus a plus equal to minus zp and y minus b similarly is equal to minus zq. Okay. Now we want to eliminate a and b, so let us square. So then x minus a whole square plus y minus b whole square will give you z square into p square plus q square. Now by the given relation x minus a whole square plus y minus b whole square is equal to 1 minus z square. So 1 minus z square equal to z square times p square plus q square, and therefore we can write it as z square times p square plus q square plus 1 equal to 1, and it is not a linear equation in p and q. Okay, now classification of PDE of first order. So let us look at the first order partial differential equation and discuss their classification. The first order partial differential equations are classified in accordance with the form of the function f in the equation 1. Okay. The classification of the first order PDE will depend on the form of this function f, f(x) by z pq equal to 0. Okay. So if this the first order PDE is of this form, px by z into this is p, okay, this is p, qx by z into q equal to rx by z, then such a partial differential equation of first order is called as a Cauchy linear PDE of first order. Here the coefficient of this p, small p and small q can be functions of x by z, and the right hand side rx by z, okay, which is free from p and q, can also be a function of x by z. So if the coefficients of p and q which occur in first degree and separately, okay, their coefficients are functions of x by z, and then the right hand side rx by z is also function of x by z, then this partial differential equation is known as Cauchy linear partial differential equation of first order, where p and q are linear and the functions p, q, r depend on the independent variables x, y and the dependent variable z. Now if the coefficient of p, this is p, this is q, and if the coefficient of p and the coefficient of q are independent of z, they only depend on the independent variables x and y. So the coefficient of p is a function of x, y only, the coefficient of q is a function of x, y only, while this term which is free from p and q is a function of x, y and z, then such a equation is called almost linear partial differential equation of first order. Now if we have an equation of this type, where the coefficient of p is a function of x, y, the coefficient of q is a function of x, y and z, okay, z which occurs in first degree, okay, is a the coefficient of z is a function of x, y equal to a function of x and y. The term which is free from p, q and z is a function of x, y only, then such a partial differential equation is called as a linear partial differential equation of first order. So here the function f which occurs in f(x, y, z, p, q) equal to 0, if this function f is linear in p and q, p, q and z, while the coefficients a, b, c, d depend on x and y only, then we shall call it as a linear PDE of first order. A PDE of first order is called non-linear if it is not a PDE of any of the above types. Okay. So, like for example, you can see now let us look at this examples. X square, this is P, this is Q, okay, and then we have x plus y into z. This PDE is of the type AXY into P, BXY into Q minus plus CXY into Z equal to DXY. Here AXY is equal to x square, BXY is equal to y square, and CXY is equal to minus x plus y, while DXY is equal to 0. So, it is a linear PDE of first order. Here x P plus YQ equal to Z square. This PDE is of the type AXY into P plus BXY into Q equal to RX by Z. Here the coefficient of P depends on x and y, the coefficient of Q also depends on x and y, while this term depends on x by z. This is so AX by here is x, BXY is equal to y, and RX by z equal to z square. So, this is an almost linear PDE of first order. Okay. Now, let us look at this. Here the coefficient of P is Pxyz equal to y plus zx, coefficient of Q which is Qxyz is equal to minus x plus yz, and Rx by z is equal to x square minus y square minus z square. So, this is a Cauchy linear partial differential equation. The coefficients of P and Q depend on x y z, and this term, okay, Rx by z also depends on x y z. So, it is a Cauchy linear PDE of first order, and this equation you can see this is a partial differential equation of first order, but here P and Q are not of first degree. So, this is P square plus Q square into y equal to z into Q. It is not a linear PDE of first order, non-linear PDE of first order. Now, let us see how the partial differential equations are formed. So, let u be a function of x by z, b be a function of x by z, and further assume that f u b is equal to 0, that is there is a relation between u and b which is given by the function f. So, f u b equal to 0 and f is arbitrary. Then differentiating this equation, okay, differentiating this equation with respect to x, what we shall have, u v are functions of x by z. So, we will have partial when we differentiate with respect to x, partial derivative of f with respect to u into derivative of u with respect to x plus derivative of u with respect to z into derivative of z with respect to x plus derivative of f with respect to b into derivative of b with respect to x plus derivative of b with respect to z into derivative of z with respect to x, which is equal to p equal to 0. So, similarly, when we differentiate this with respect to y, we get yeah. So, when we differentiate f with respect to u x, we get partial derivative of f with respect to u, then we have to differentiate u with respect to x. So, derivative of u with respect to x plus derivative of u with respect to z into q into p, and then we differentiate f with respect to b. So, partial derivative of f with respect to b into partial derivative of b with respect to x plus partial derivative of b with respect to z into p equal to 0. Similarly, when we differentiate this equation with respect to y, we get f u into uy plus uz into q plus fv into vy plus bz into q equal to 0. So, we get these two equations, and when we eliminate fu arbitrary derivatives of the arbitrary function f with respect to u and b as we had discussed earlier, okay, this will give you the following. This determinant equal to 0, and you can write it as in the form of a matrix equation, where the coefficient matrix will have this element a11, then a12, a21, a21 multiplied by the column vector fu fb equal to 0. Okay, we can write this as a matrix equation like this. So, ux plus uz into p, and then we have uy plus uz into q, and then bx plus bz into p, and by plus bz into q multiplied by the partial derivatives fu fb equal to 0. So, we will get this. Now, this matrix equation will have a non-trivial solution provided the determinant of the coefficient matrix is 0. So, we will have ux plus uz into p, uy plus uz into q, and then bx plus bz into p, by plus bz into q equal to 0. So, when you put this determinant equal to 0, we arrive at this equation, p times this, q times this expression equal to this expression, and which is nothing but in the form of Jacobian we can write it as p into del ub over del yz plus q del ub over del zx equal to del ub over del xy, and if we denote it by p, this by q and this by r, then we have pp plus qq equal to r, which is a first order partial differential equation which is linear in p and q, because p and q occur in the first degree. It is called as Lagrange PDE of first order. Now, let us consider some examples to illustrate how partial differential equations arise as a result of eliminating arbitrary constants and functions. For example, let us consider z equal to f x plus I t plus g x minus I t, where x and t are independent variables, z is a dependent variable, f and g are arbitrary functions, I is iota, that is square root minus 1. So, when we we have to form the partial differential equation by eliminating the arbitrary functions f and g here. So, let us differentiate it partially with respect to x. So, p will be equal to f dash x plus I t. We can take x plus I t as u. Okay. So, f dash u into partial derivative of u with respect to x, which is 1 plus g dash x minus I t, x minus I t we can write as v into partial derivative of b with respect to x. So, we have 1, and then we can this is derivative of z with respect to x. Now, we can take one more derivative with respect to x. So, second derivative with respect to x will be equal to this is f prime u is x plus I t. Okay. So, f double prime x plus I t into 1, and here we will get g double prime x minus I t into 1, because v is x minus I t. When we differentiate v with respect to x, we get 1. Similarly, if you differentiate it with respect to y, differentiate this equation with respect to t. Okay. Differentiate this equation with respect to t, what we get f prime x plus I t into I. Okay. And then g prime x minus I t into minus I. When we differentiate it once more with respect to t, what we get f double prime x plus I t into I square, and here g double prime x minus I t into minus I whole square. So, this will be minus f double prime x plus I t here plus g double prime x minus I t. Now, let us call it equation 1 and this as equation 2. So, when you add 1 and okay, we have this will be okay. This is I square, this is also minus 1. So, we get minus f double prime x plus I t minus g double prime x minus I t. So, when we add the equation 1 and 2, this is 2, okay. 1 and 2, the right hand side becomes 0. This will cancel with this will cancel with this, and we will get z x x plus z t t equal to 0. So, this is a second order partial differential equation we get. Now, let us consider the equation a x square plus b y square plus z square equal to 1. Then we differentiate it with respect to x, we get 2 a x plus 2 z p equal to 0, or we can say a x plus z p equal to 0, and then we differentiate with respect to y, we get 2 b y plus 2 z q equal to 0, or we get b y plus z q equal to 0. So, we have a x square plus b y square equal to 1 minus z square. So, what we do, we multiply this equation 1 and 2 y x. So, 1 into x and 2 into y, and let us add them. What we get, a x square plus x z into p plus b y square plus by z into q equal to 0, or we can say this is a x square plus b y square is 1 minus z square. So, we get x z into p plus by z into q plus 1 minus z square equal to 0, or we can say this is z times x p plus by q equal to z square minus 1. So, this is the PDE that we get when we eliminate the arbitrary constants a and b here. Now, let us look at this f x plus y plus z x square plus y square plus z square equal to 0. We have an arbitrary function f here. So, we have to eliminate this arbitrary function f. So, let us take u equal to x plus y plus z, b equal to x square plus y square plus z square. Then f u v equal to 0. So, let us differentiate this equation f u v equal to 0 with respect to x. What we get? Partial derivative of f with respect to u into partial derivative of u with respect to x plus partial derivative of u with respect to z into partial derivative of z with respect to x plus partial derivative of f with respect to b into partial derivative of b with respect to x plus partial derivative of b with respect to z into p equal to 0. Similarly, when we differentiate with respect to y, we get partial derivative of b with respect to z into q equal to 0. Now, u is x square plus y plus z. So, u x is equal to 1, u y equal to 1, u z is equal to 1, okay. And b x, partial derivative of b with respect to x is 2 x, b y is 2 y, b z is 2 z. So, when we put the values here, what we get? We have f u multiplied by u x is 1 plus u z is 1. So, we get 1 plus p plus f b multiplied by b x is equal to 2 x, b y is equal to b x plus b z is equal to 2 z into p equal to 0, and then f u times u y is equal to 1, u z equal to 1. So, 1 plus p, sorry, here we have q. So, 1 plus q and then f b multiplied by b y is equal to 2 y plus 2 z into q equal to 0. Now, we can eliminate f u f b from here. So, 1 plus p 1 plus q and 2 x plus 2 z q, here we have 2 y plus 2 z q equal to 0. So, when you expand this determinant, you arrive at this equation p times y minus z plus q times z minus x equal to x minus y from here. Now, when we have z equal to x y plus f x square plus y square, when we differentiate partially with respect to x, we get p equal to y plus f prime x square plus y square. So, we are differentiating f with respect to x square plus y square into 2 x and then q equal to x. When we differentiate with respect to y, then we have f prime x square plus y square into 2 y. So, we can write p minus y upon q minus x equal to 2 x over 2 y or x over y. So, we can divide and f prime x square plus y square will cancel and we will arrive at this equation. Now, similarly z equal to f x y over z, when we differentiate it with respect to x, we get p equal to f prime x y over z into derivative of this with respect to x. So, derivative of this with respect to x means what? We have to differentiate x y over z with respect to x. So, we will have the derivative of the numerator will be y into z minus derivative of z with respect to x, that is p into x y divided by z square. Similarly, when we differentiate with respect to y, we get this derivative of numerator with respect to y. So, we get x into z minus q into x y over z square. Now, we can divide to eliminate f prime x y over z and we will arrive at p x equal to q y. And if we have the PDE of family of planes, the sum of whose x y z intercepts are is equal to unity, then the we can write suppose the intercepts let us say by the plane, let the plane be x over a plus y over b plus z over c equal to 1. Now, this plane makes intercepts a0, a, b and c on the 3 coordinate axis. We are given that the sum of whose x y intercepts, x y z intercepts is equal to unity. So, a plus b plus c is equal to 1. This is given to us. We have to arrive at this PDE. So, let us differentiate this with respect to x. We get 1 by a. Now, this derivative of y with respect to x is 0. So, 1 by c derivative of z with respect to x, we get p equal to 0. When we differentiate with respect to y, we get 1 over b plus 1 over c into q equal to 0. So, we get the relations, we get p equal to minus c over a and q equal to minus c over here we get this is b. So, q equal to minus c over b. So, p is minus c over a, q is minus c over b. Okay. Now, we want to find this relation here. So, a plus b plus c is equal to 1 gives you when we divide by, let us say here we have minus c y, or we can say 1 by p is equal to minus a by c and 1 by q is equal to minus b by c. Okay. So, a plus b plus c is equal to 1, we can divide this equation by c. So, a by c plus b by c is plus 1 is equal to 1 by c, and what we get here a by c is equal to minus 1 by p, b by c is equal to minus 1 by q plus 1 equal to 1 by c. Now, we have to eliminate 1 by c, and to eliminate 1 by c we take the help of we take 1 to eliminate 1 by C. What we will do, this is here we have PQ LCM minus Q minus P, and then we get PQ equal to 1 by C. So, we get PQ upon, or we can say C equal to minus PQ upon P plus Q minus PQ. Now, let us find Px plus Qy minus Z. So, this is Px plus Qy. P is equal to minus C by A into x, Q is minus B by C minus C by B into y minus Z we have. Now, this is minus C times x by A plus y by B plus Z by C, and we are given that x by A plus y by B plus Z by C equal to 1. So, this is minus C. So, Px plus Qy minus Z is equal to minus C. So, what we get? We have minus C equal to PQ upon P plus Q minus PQ from here, and from here minus C is equal to Px plus Qy minus Z. So, we get this partial differential equation. You can see it is non-linear. Now, with that I would like to conclude my lecture. Thank you very much for your attention.